Right, good morning, everybody, and welcome to the first WebEx version of the class. We actually are going to be one lecture ahead beginning next week because the university's closed on Monday, and so once we have our Tuesday lecture in person on campus, we'll be one ahead. So what we'll do is cover just a little bit more detail and maybe go left and right a little bit to some related topics while I work fast to catch up the Monday, Wednesday group, because I will lose my mind if you guys are not in sync for the rest of the semester. And then I think the reverse happens later in the semester, but to kind of keep the total number of lectures even for both sides. But I'll do the same thing in reverse when we get to that. So we have a pretty big chapter in Chapter 1. This is one that takes a very broad view across what's going on the network, and quite a bit of detail on the little bit of the history and sort of what's happening with the standards groups. There's more on that in more advanced courses, but this is our chance to get exposed to some of that. So we'll go a little bit beyond what the book talks about and go into a little bit of discussion on what's happening in the standards groups by borrowing a few slides from another from another text. So I'm going to in fact pull that up to have it waiting on the side here so we don't have a lot of delay. All right, I've got that up where I want it. So what we're basically concerned with here is the getting past the spectrum stuff. We talked about that last time and we looked at all those maps. Oh, one fun thing to look at is this is US, Canada, Malaysia, Mexico, South Africa. You notice they all kind of look the same. The tools that are developed to kind of lay this stuff out is similar across the world. Not surprisingly, it's the same spectrum after all. So there's an industry of consultants and businesses that kind of help and aid countries and their regulators into pulling these maps together and pulling good regulations together so people are enforcing things and writing things technically enough in consistent fashion that manufacturers don't go crazy trying to figure out how to adjust what they do country by country. One of the fun things I ran across at some point ago was a survey that the United States NTIA did to try and understand, are people actually using these licenses and are we seeing spectrum being consumed and occupied in accordance with the license plan? So it's not in fact, it's the only one I've actually seen a detailed report on. I don't think they happen very often. There was a guy in Atlanta, and I may have told you this story already, who figured out how to develop a cell blocking technology and put it in his station wagon. And when he would drive to work in Atlanta, he'd turn this thing on so nobody around him could be on their cell phones texting or talking. My personal opinion is it probably just makes you focus on it even more, like what's wrong with my phone? But people would complain that calls would get dropped, et cetera. And it took years, but they finally set up the right testing equipment and caught the guy. And it was a $64,000 fine for him. I don't think he went to jail or anything, but he did, of course, become everyone's hero in the technical community as well. So I see Jeffrey and Aaron are having like a chat conversation about audio. Aaron, would you mind if I could impose upon you, drop Jeffrey a hint on what to do to get connected to audio? I don't know whether he's on a mobile or a laptop, but that would be huge. So here's the truck they used. They hoisted a couple of antennas. They weren't too far from Midway Airport, and there's a little map of where they planted this stuff. And so they used lots of tools to kind of scan through all the frequencies and figure out what people were doing. And so here's a snapshot in this giant report, and I gave you the URL if you want to go dig around in it. And what they're trying to find is what's the level of background noise, what's the signal strength, and they can't tell who's doing it necessarily, but they certainly can tell what direction things are coming from and try to get a little bit of an idea of what's happened. They looked at LTE signals, for example. Those are ones that are particularly of concern along with military frequencies because the government charges those companies billions of dollars for those frequencies, and they expect the government to kind of keep them clear of chatter that's not important. All right, so we'll blast through that a little bit. There used to be a really cool site up called the Spectrum Dashboard, and it's not been updated in a while, but it's still was out there. But sadly, if you go today, and this is not going to be a surprise to anybody, all you see when you go to, see if I can find reboot.fcc.gov, kind of a bad name for something given what's going on, but all you see is this lapse of funding statement. If you go to the NTIA, hold on, don't want to do that. If you go to the NTIA and the frequency allocation guys, that's not the right one. I do this every time. I fall for it. I go to this is the one that's for sale. It's a .gov. It's not a .org. So they have a lapse in funding, but they do have a link to the frequency allocation chart. And the same thing is true if you start going around to some of the other organizations as well, like the National Institute for Standards and Technology, which keeps track of some of this stuff as well. So it's kind of a downer, and it makes it a little harder to give homeworks that have you go and survey some of this stuff. But I think I can still piece together enough to make it an interesting journey for you guys. Give you a chance to learn. One of the things that's important is there are text data of all these licenses, and bidders do things with them. You can do things like search for all of the LTE licenses in a certain range in the Houston metropolitan area, and you can get a list of everybody who's got one of those licenses, what the license number is, and that sort of stuff. So you can get an idea of what the competition is if you're thinking about going into a market. So the bulk of what we need to get covered today is what's in this chapter, and with a little luck, we should be able to finish it as I polish off the last little bit of my croissant that's just been staring me, and I can't resist anymore. Sorry about that. We're going to define what the internet is, what the difference is between a protocol and a standard. We'll get a little bit technical on that, and we'll look at what's occupying the network, what do we call the components, how do we classify them, what connects these things together, the measurements that decide whether you're going to have a great day or a crappy day on the internet today. And so there's just a few metrics really that make the most difference. And then we'll touch a little bit on some of the stuff for security, and we'll veer around on that a little bit to pull up tools like Wireshark and capture some packets during class and take a look at them. So I'll start doing that. Most lectures will have an opportunity to pull that up. We'll have a good reason to pull it up, and it'll help get you guys a little more acclimated to it. And you'll have a Wireshark assignment in your first homework as well. So what is the internet? Well, the nuts and bolts parts are we have three classes of devices. First are the hosts. These aren't just PCs and laptops. This is everything that's hanging off the edge of the network. Because as far as the internet's concerned, the core is all of the equipment that forwards information around, and the original, the ultimate destination point and the origination point of all of that information comes from all the computers hanging off the edge. Phones, tablets, laptops, Internet of Things devices, large data centers, mega servers, supercomputers, all of those things are hosts. And we don't distinguish between PCs and servers in that environment. So that's a little tricky, and host sounds like it might be something small, but just think about it from the internet's point of view. And we also will call those things end systems. And what makes them capable of working on the internet is somebody's bothered including in their code functions that were part of a socket library, and that's generally what people call it. And there are versions of socket libraries built into absolutely every operating system, because who has an operating system that they want to use that can't get to the internet, right? So these socket libraries, and we'll have a chance to look at some of these things as well, they give you function calls. And the function calls do things like let you specify the host that you're trying to get to. You don't have to tell it who you are. That'll get added in for you later automatically. The information that you're trying to send, the actual data, so maybe it's like the contents of the web page or the contents of the email or the chat message that you're sending, those are things that you pass along as an argument. So the application you're running, the program you sit down and run as a user, is what is making this call. So if you run your browser and you click on a URL, it's going to build a message using this library, and inside the info part of that message is going to be a well-formed request for a web page that presumably only the server at the other end knows how to interpret. I mean, the rest of your computer could look at it and it would go like, I do not know what this means in the info section here. It's just data. I guess my job is just to pass it along. And then sometimes you have some options that you can specify. It turns out there's two big classes of ways of doing this. One of them bothers to do a whole bunch of housekeeping and keep track of your packets to make sure if one doesn't make it to the other end, it resends it so it'll remember it. And the other one couldn't care less. It just, thank you, sends it, throws it on the network, doesn't care if it's congested, doesn't check if it's okay to send stuff, just does so. And there's good use cases for both of those. So that's part of what we, again, call a socket library. And so if you include a socket library in your code, then you are said to have a network app. So destination, and what would the other parameter be? If this is destination, then this one would be source. Ta-da! Ding, ding, ding. Winner, winner, chicken dinner. Okay, good. I'm watching the chat over to the side. So they talk about communication links next, but I think that's a little backwards for me, so I'm going to switch down to the endpoint, and then we'll come back to communication links. The stuff in the middle of the network that once you've created a packet, you need to hand it to someone to kind of get it on its journey. Sort of once you've left your house and you have your suitcase and you know where you're trying to get to, you start by getting in a car. It could be a taxi, but you begin the journey across this road network, and at every intersection you're going to get pointed in one direction or the other, probably by Waze. And there's an analog to that. And the analogy on the internet are packet switches. We call them routers almost universally. So you'll hear me refer to these probably for the rest of the semester as just routers. Switches are not found in the core of the internet, but they are found all over institutional networks because they're less expensive than routers, and they can do some of the things to kind of get you pointed in the right direction and make basic decisions about whether traffic needs to leave the local network or not, for example. So there are millions of these. They're owned by anyone and everyone. Some of the ones at the core are owned by big telecommunication providers. Some of the tier 1 providers you've never heard of before because they have names that are only known in the industry, but they don't sell anything to people within systems, so why would you ever bump into them? But there are also people who own routers that, like your ISP, and they give you one when you sign up for your internet service. So that little box you have at your house, among other things, is a router as well. So what connects the routers to each other? What connects the routers to users? There's some type of communication link. And they began as just copper, and then radio, and then fiber, and then satellite. And I think actually satellite may have come out before even fiber was very popular. But they all have certain characteristics, certain capacities and capabilities. One thing they don't have, which the terminology we use to describe the behavior of networks unfortunately leads you to believe that they do, is none of them have the ability to change the speed at which information travels across the network. They all run as close as they can to the speed of light. We don't really get to change that. That's kind of been decided by nature. So once you get a bit, once you figure out how you want to encode a 1 or a 0 on your sine wave, and let's say you decide you want to make a little dip like this, and we're going to make this represent a 1. Once you've emitted that and inserted that voltage signal, that pattern, onto whatever the media is, copper wire for example, it will travel across that wire near the speed of light. So when we talk about how fast a network is, we're really not talking about how fast the network is. We're not talking about the speed that things travel across the network at all. Not like we would when we talk about how fast a plane is, or how fast a car is, or how fast do you eat. It's not speed. What we talk about when we say the speed of a network is from the time you decide that you need to insert a bit or a string of bits onto the network, how long is it going to take you to encode this signal? Part of it has to do with how close together these humps are in this sine wave. If they're very close together, then you know you'll be able to do one here, and then in very short order you'll be able to do another one at the second hump. If it's a very slow wave, then maybe the time is different, but then again maybe you encode it in a different way, and maybe your signal looks more like that instead of this, so that you can get lots more bits on there. There's lots of technologies. This is what network technology designers spend their whole careers worrying about. The electrical engineers around us crank out amazing new innovations, and there's been just tremendous progress made from having fast electronics that can filter out noise and re-encode things and switch to other frequencies. And so that's made things like Wi-Fi even possible. But if you tell me how many bits you can encode in a second on this network, where each bit travels at the speed of light, the perturbed sinusoidal wave travels near the speed of light to the other end. If you tell me how many times you can do that in a second, then I'll tell you the bandwidth of your network, how many bits per second you can send. So bandwidth is maybe perhaps a little better term for this, but even bandwidth suggests like how wide, how many lanes wide is the road, how wide is the network, how many bits can you send at once? The answer is always exactly one. You can send one bit at a time. You can encode one thing at a time. Now you can get tricky, and we'll look at that when we see some information from another textbook to talk about information encoding. But just remember, speed of the network never is talking about like it means when you talk about speed of your car. It's talking about how many bits can you insert on the network to begin their light speed journey to the other end. All right, so that's confusing for a lot of people. Lots of crazy devices out there now. We will be overwhelmed by these if we're not going to be this year already, because we're inserting computing in small devices everywhere. Some of these are small, non-standard based, non-desktop-like chip systems, embedded, customized SIMs and chips, and systems from people like MIPS. ARM is becoming very popular. That is absolutely standard. What I'm really talking about is there are a lot of these things that are maybe that big and run Linux and have Ethernet or Wi-Fi or Bluetooth. You can connect to them by a USB cable to your laptop and then use your screen, keyboard, and mouse to control them. And they have storage, so they have all the checkbox items to make them a full-blown computer. And we can build some of these now for $1. So that's what's going to be flooding the network, and we're going to have a lot of work cut out for us to try and keep them from basically overwhelming and swamping what goes on. So we'll spend some time talking about that as well. So the Internet, therefore, with the capital I, is a network that is comprised of millions of these smaller networks, all of whom have agreed to follow the standards and interconnect with each other for the purposes of exchanging traffic. They may do it for free. They may want to charge. In the early days, people used to all connect to a service called UUNet, and one of the things they offered were lots of these bulletin board type systems, news groups, and they in turn, of course, connected to lots of other people. So one thing people used to do is feed them traffic that really wasn't destined at all for anything that UUNet provided. They just wanted them to carry the traffic for them out across the network and give it to somebody else. So they quickly decided, we're not going to transit your traffic for free. We're going to charge you to do it. So if you do need to get your traffic out of your network and you're not going to buy internet service from a provider, you can just buy transit service from someone, and it's essentially the same thing. And if you go to very many of these websites like mxtoolbox.com, for example, very often they'll throw ads up on the sides. Let me see if I can find we can find some transit costs. Here we go, IP transit. I just saw it at the bottom there. This is an ad that pops up. These guys pop up their ad all the time. So Hurricane Electric. Anybody here heard of them before? It's not an electric company. Don't call them when you need to get your cable redone for your lighting system. They are a very large IP transit provider. So let me switch over and show you Firefox, and I'll show you what I'm talking about here. So I've gone to Hurricane Electric, and I pulled up their 3D map. I'll go back so you can see where I did it. So here's the 3D network map. You pull it up, and you basically can see their depiction of sort of the traffic they're carrying and where things are being traveled around. And these little submarine icons here are intended to represent submarine cable routes. So if I can find where we are in here, and I think I just moved back, that's Honolulu, so we're getting warmer here. So you can see there's some undersea cables off the coast of the United States. There's lots of traffic around here. We're a landing point for an undersea well, probably a terrestrial cable for the most part that goes to Miami, and then lots of things leave from over there. If I can find the site up still, there's a tool and animation that shows you how this has evolved over time that's really fantastic. So there are lots of places out here that will show you sort of what's going on. They also have satellite connections that they're showing you here. So that's what these guys basically do, is you can feed them traffic. Once it's on this network, they'll get it to wherever it needs in the world, and they charge you by the amount, the quantity of data that you send. And they usually throw ads up that say where they're at. Now they also have a list of transit service locations, and we're going to come back to that in a minute. Okay, so continuing on, when you want to get people to write code that performs the same task for enabling communication between two devices, you need to set up some rules, just like you do with a language. So if I knock on your door and say hello, then you say something back, or if I meet you on the street, I don't maybe just ask you for money, maybe I say, excuse me, can I interrupt you for a minute? So there's protocols that we've developed, largely unspoken, that teach us how to behave, and they govern the rules and the syntax and the actions we take based on what's being said. And we've got to be very specific about that when we get on the network. And so when you have such a combination of things, you are said to have a protocol, particularly when it's exchanging bytes of information between computers. There's standards for lots of other things that we'll talk about, but I'm talking just for a moment about protocols for communication. You write it up, you publish it in a particular group called the Internet Engineering Task Force, and people get a chance to review it and vote on it. You get a couple of chances to get enough votes that say this is a good thing for it to continue down the journey. And if you can't get you get 2 chances in 6 months. If you can't get it done, it's dead. And when you publish these documents, you're asking for people's comments on them. And so they're called requests for comments. And no matter how far they get through the standards, they're still always called just RFCs all the way to the end, even when you're not asking for comments anymore. So it's kind of funny that they still call it that. And the group that's responsible for that is the Internet Engineering Task Force. So I'm going to switch gears and show you a few slides on how that is organized that I mentioned I would do from another text. So here's the process that an RFC goes through. You publish it as an internet draft. It becomes a proposed standard. You get 6 months and 2 tries to become a draft standard, 4 more months and 2 more tries. And if you pass that, then it becomes an internet standard. And this is a big deal because they can require everyone change their code. Every host system or every packet switch, every router change their code. So there's lots of people who are interested in having a say in it, and there's lots of organizations who participate in the group that manages this process, thousands of people, in fact, from all over the world. Once a standard has run its course, sometimes they don't make sense anymore and they'll move to a historic status as well. But once you have a standard, it can be required, it can be just recommended, it can be elective, limited, or not recommended. A required one might be you must use this type of addressing mask because we're not going to use classful addressing anymore. A recommended standard might be something that says you should check to make sure the email message you're receiving in your email server that claims to be coming from a particular place is in fact coming from the IP address of the device that the DNS record says that particular place really is sending their email from, to prevent spam. And we'll look at both of these examples in more detail, so just kind of let it roll by for the moment for now. The organizations that kind of put this stuff together, as I mentioned, the Internet Engineering Task Force, they exist here in the corner of this diagram. At the top of them, they're run by the Internet Society. Vint Cerf is the lead of that right now. He wrote TCP, and I just grabbed a video of a talk he gave here during the summer during Networks class, and I'm going to see if there's anything fun in there that we might want to use. I don't know why my computer is thinking I'm connecting and disconnecting my phone all the time. So there are working groups in here, but that's a snapshot of the way this works. We'll take a look at the IETF webpage here in a couple of minutes, and I'll show you kind of why it's kind of a fun thing to do. So from a service point of view, not from a nuts and bolts point of view, what the internet provides are services to us. I mean, we all know that. We use it to run all of our apps and things. And those hooks that allow you to send and receive and connect, that's that socket library I talked about. So the way to think about the services they provide, it's very much akin to a road network or to a postal network. You write a note, you put it in an envelope, you put an address on the outside, and you drop it in the mail system. You don't really know the route it's going to take. You don't really care the route it's going to take, but hopefully it takes pretty good routes to get there, and it arrives at the other end in a reasonable amount of time. So that's exactly the promise the internet makes. It's a best efforts network. It does not promise to guarantee packet delivery or that things show up in order or that they're not duplicated or they're not dropped. So if you need those things to not happen to your packets, you are going to have to write code in your application or use one of the operating system transport layer services to add that extra protection. Because once you turn the packet loose, once it's on the internet will not do any of those things. It will just try to get the packet to the other end. If it drops at some point, it doesn't care. It doesn't care. All right, so we'll find out why that happened and why that's okay. So back to the protocol then. So we talked a little bit about standards and how you get something all the way through. Standards can be about lots of different things. They don't have to be just about protocols. Standards can be about the way you should handle domain names, the way you should publish who the administrator is of your network. You can have standards that govern the formats of operating system control calls, but lots of the standards deal with the actual exchange of traffic, the communication between one host and another. And so protocols basically are between machines, but we use them also between humans, and they define the format of things, the sequencing, the order, who starts, what kinds of responses are available from that. You know, if you hit the shoot button on a video game, what are the range of reactions? That's got to be written into the code. And so that's what a protocol is decidedly trying to define. So let's go look at a couple. And first I'm going to look at one that is not a communication protocol per se. We'll take a look at an old one from 1974 written by Vint Cerf, the guy I mentioned a few minutes ago. So this is where they specified a program that runs on your computer that if you hand it a packet, it will make a copy of it and give it a number and send it to the other end over the network and ask for an acknowledgement to come back to acknowledge the receipt. And if they don't get one, they'll send it again. So to you, this implements reliability, because if your packet got dropped, then they will take care of resending it again. So as you can see, it's a big, giant, long text document. They talk about various formats of things in here. They eventually get down to defining data structures and values for certain variables, what they mean. If you transmit a 0 in the type code field of the data, then it means it's a general message. If you send a 2, then it means close the connection, etc. And they dutifully just methodically go through and line out all the possible fields in this string of bytes that you're allowed to send back and forth and what they mean. So if you wanted to sit down this afternoon and write a version of this program, TCP, and overwrite the one that's in your operating system with your own, you can do it. I mean, not only do you have permission to do it, but you actually could pull it off, because all the details, every last bit of detail you need, is published in the RFC for TCP. Let's go look at another one. Let's look at one for a communication protocol run by your browser. So this is way above the network. This is an end user program that you double click on and run on your phone or on your desktop all the time. And this one is, you know, much later date, from '99. And here's Tim Berners-Lee, whose name you may have heard, is the inventor of HTTP. But there's people here from companies that are now part of HP and the University of California at Irvine and Xerox and Microsoft. And yep, that Xerox. They're actually very important in the history of computing. So this is not the original version of HTTP 1.0, this is the follow-on version. So they walk through and give some justification. This one's a little fancier. They have hyperlinks for some things, but I want you to see it's 176 pages long. So if you want to sit down and write a browser this afternoon and teach that browser exactly how to put a string of bytes together that, if sent by the network to a server, will be correctly interpreted as a valid message requesting, say, a web page, for example. This document will tell you exactly how to do that. And so people that want to write browsers can start with this. They start defining terms again. It's a very similar kind of thing. They have names for things like servers and the age and the timestamp and what transparency means. They give you an idea of the sequence of commands and sequence of communications that go back and forth. They eventually get down and start defining things like syntax. So if you need to parse out what's arrived in one of these packets, here's how you figure out the first 3 bytes are supposed to be the date, and the next 5 bytes are supposed to be the language, and so forth. This will help you do that. They define types of data, and then they start defining values. So if you want to send a separator, here's the valid separator strings. And let's get down and look at date and see how they defined date in here. And I think I'm really close to it here. So there are 3 valid formats for time stamping something in an HTTP message. And you'll use this to say how old the page is, for example. But there are 3 of them. One of them is defined by RFC 1123, another one by RFC 1036, and then there's a third one which is kind of the ANSI National Standard AFC time. And you can use any of those 3. So HTTP date as a variable, therefore, is defined as this type of variable or this type of variable or this type of variable. Those are the 3 things that we just looked at up above. If you choose the first one, if you choose to send a date in this format, then it's going to be comprised of a weekday followed by a comma, a space, date 1 space, time space, and then the string GMT in uppercase. So what's weekday? Well, weekday is a 3-character string with the first letter uppercase, and here they are. What's date 1? It's a 2-digit with space and a month. So for example, 2-digit day, a space, 3-digit month, a space, and then a 4-digit year. So you could write the code from this. You could sit down and write the code to crank out a valid date based on what you're reading right here in this RFC. So that's basically the idea. And you can see we're only on page 22, and this thing goes on and on and on and on. And there's no pictures. There's no animations. So if you really want to do this, you're better off starting with this, but then diving into YouTube and Stack Exchange and going to a class and talking to people, because this is, really hairy. I don't envy anyone who decides they want to sit down and kind of try to go through this stuff. So those are a couple of RFCs, and in the second case in HTTP, we were defining the protocol that a web browser uses. So that protocol is not running in the routers, and it's not really running inside your operating system at all. It's just something that's running on your application. But because this application is so popular, they decided to publish for the world the protocol so anyone could write server code or browser code at any time they wanted to. Right? So that's why things like that. Skype, on the other hand, as a counterexample, does not publish what their algorithm looks like. They write on top of that first one, TCP, but they just hand it data to send, and they say, don't you worry about what's in that data. Just send it to the other end for me. Be a good little boy and send that over for me. But they don't ever publish in an RFC the structure of that data, the format, how you interpret it. They don't talk about the compression algorithms they use or how they decode things, because that's a proprietary advantage for them. It's a commercial product, and that's perfectly okay. You can do that as well. So much like saying hello and asking for the time, computers will send data back and forth. On the right, you see an example of a computer that wants the data to be sent reliably, so they're going to start by handing their data to this program called TCP, which we'll talk a lot about this semester. And TCP, in turn, is a very polite protocol. It will start by asking permission of the server. Like, I have stuff to send you. This user doesn't want it to get lost. So I guess the first thing I better do is figure out, are you there? Are you awake? Are you able to take another connection? Do you have any buffer space if I start sending you stuff? May I have a communication with you? And if it says yes, then you can send, in this case, a URL for a web page that somebody's looking for. Okay, so there's lots of other protocols here. And one of the things I want to spend a couple of minutes on is the history of of one of the protocols that we use without ever thinking about it, and that's how we use the telephone. The telephone was invented at a time when it was polite to be introduced to someone new, not to approach them on your own and say hello. So you would have a friend introduce you, and you still see this in very formal settings, like at graduation perhaps, or something at a high level of business, or maybe a wedding. May I introduce you to my nephew, Bob? He's in college at the University of Houston, etc. But back when the phone was first invented, that's the way society expected you to be introduced to people. So this is a problem for people trying to put this phone network together, because who's going to do the introduction? Do you need 3 people on the call then? Do you have to find someone that you know that has a phone that also knows the other person? How long is that going to take to build that business? So they wanted to teach people to get past it. So the first thing they had to do was teach you to pick up the phone. So I don't know about you, but my intuition probably would not be if I have this strange looking box that starts making noise and then stops for a little bit and then starts making noise again, ringing, in other words. I don't know that my first intuition would be to go up and to start to dismantle it by taking part of it off. I might run. I'm a little bit paranoid. I might think like, what is this thing? So they had to get over that. First, they had to teach people how to do it. And then when you picked up the phone, they had to teach you to do the opposite of what you'd learned to do your whole life, which is you start talking. So if I come up and knock on your door and you open the door, it's expected I'm supposed to say, "Hi, sorry for the interruption. My name's Kevin. I just noticed your dog was loose in the yard, blah, blah, blah," right? So the type of communication we want to have happen on a telephone is sort of in reverse of that, right? You're the one that got called, and yet when you pick up the phone, you're supposed to start the conversation. Well, what conversation is it you were supposed to start? It wasn't your idea to start the conversation. They called you. Shouldn't they start? So you had to teach people to say something. And then the last part of this, which is kind of a fun twist, is you had to be taught how to start the conversation. And remember, the phone company is spending money while this is all going on. You're using their network, but you're not generating any revenue for them yet, because they can't start charging you by the minute, which they did for 100 years, because you haven't really started a communication yet. You haven't started a conversation. The ringing and setting up the lines, all that stuff is sort of included in a base cost. They don't make any extra money for that. So you're just tying up their network. So they don't want you to give a long-winded introduction. They want you to say one word. And they invented the word hello. The phone company, AT&T, invented the word hello. There was a huge debate over what word to use, but they eventually settled on one that was similar to what ferry boat captains would use to hail a ship coming into port to see if they needed help getting guided into port. Allo. So they used hello, and interestingly enough, many years later, I heard a story by a guy who was looking for someone who may have attended the first telephone operators convention in history in Niagara Falls, New York. Why? Because they were the first people to invent the "hello, my name is" badge, because they invented the word hello. In English, and only here, we use the same word to greet people in class, on the street, in everyday life. But in lots of other countries, the word, which they also had to invent a word there, or at least point out one of the existing words and set it aside for this use, you don't use that word in normal public. You only use it on the telephone. So in Mexico, for example, when you answer the phone, you say bueno. But you don't walk up to people on the street and say bueno, or you don't say bueno to your professor when you come into class. You say buenas tardes, hola, qué tal, or something like that. In France, you say bonjour on the street when you meet someone, but you don't say bonjour when you pick up the phone. You say hello. So it depends on the country, and this is true in other places around the world. So it's an example of a protocol that someone had to develop. They've been around forever. They've been involved in technology as long as we've had it. The internet did not invent this concept. It's just taking it further and giving you a lot more detail about this stuff. So back to the core of this thing. You've got the devices at the edge with your clients and servers. Some of these things are in data centers, but those are all hosts. They're all end systems. That's the other name we call them. The things that connect these together, we talked about were access networks, and we spoke a little bit about those. At some point down, if you go down deep enough, it's a dedicated point-to-point circuit. It's not shared with anyone else. So this circuit right here that you see, it surely is carrying traffic for lots and lots of users. So in some sense, it is a shared infrastructure. But what is not the case is if you look at what's going on this line, there's only one person generating the sinusoidal signal going left to right, and one person sending the signal that goes right to left. And it's the two communication cards in the edges of each of these routers. And it's not shared with any other devices, only those two. So as far as the communications industry is concerned, this is a dedicated leased circuit that you will pay a flat fee for every month, and it will be only you who gets to use it. So it's all you. So whatever the capacity of this network is, you're not going to get charged by the volume of data that you send or how long you use it. You're going to get charged for the whole month. So for that reason, network managers like for these things to stay full because that's how they get efficiency with their expense. That's never changed in 150 years, and it won't. So if you want to buy a different type of service, one where you get charged by the number of packets that you send, you can certainly buy that and find someone that will sell you a service, but you will reach them with a dedicated point-to-point circuit, and then once you get to them, then they will carry you maybe over a much larger area which you might have had to buy circuits for, but which they're now just going to charge you by the packet. So think about the driveway. You pay for the driveway all on your own to go from the edge of your garage to the street. That's 100% yours. It's dedicated point-to-point from the edge of your garage to the seat. It belongs to you. You have all of the expense for it. But then once you get to the road, then you pay a flat fee with your car registration and your license plate fee every year, and you can drive as much as you want. So they're not going to meter. If, on the other hand, you are in a rental car, you don't want to have a car that way, they may charge you by the mile. They may charge you how you drive. So lots of similar models with transportation networks as well. And at the core are these interconnected routers. Some of these providers in the middle, they don't allow any hosts to attach. It's just all routers. So how do you get connected to this thing? What's happening at the edge? Well, these are generally referred to as access networks, sometimes called last mile networks or first miles, what they really should call them, but they don't. And this is the technology that is very heavily regulated at the state level and somewhat at the national level, because this determines which members of the population, which citizens in society can actually take advantage of this service and not. So it's considered to be, telephony, for example, is considered to be utilitarian enough that there's enough public benefit to society in general for people being able to communicate electronically to ask for help, or for a farmer to get a price on grain, or for you to order something over the telephone, that the government stepped in and they asked companies like AT&T, look, we want you to promise to provide 100% of the citizens with telephone service, no matter what it costs you to reach some of them. So if there's a rancher 50 miles outside of Houston and it's going to cost you $1 million to run all the poles and the cable, and he's the only customer out there and you'll never make your money back, we still want you to do it. And in return for that, we're going to let you charge everybody a rate that covers the average cost, plus a little bit of profit for you. So we'll give you a monopoly, and in return, you need to agree to provide universal service to everyone. This is the way the post office works, the electric company works, the water system works, and it's the way the telecommunications networks have worked, particularly just for base telephony, for a long time. It's a little less regulated now that we have these optional services like wireless. I mean, you don't have to have wireless to be able to talk to someone. You can use an old telephone if you want. So for that reason, these things, they let the phone companies innovate more and charge basically what they want. But whatever the technology is, whether it's based on wiring or over radio waves, it's considered to be a local access network. And there needs to be a regulatory environment that encourages enough investment by the providers that people that want to get connected can. And if you can't, you're going to complain, and your politician's going to hear about it, and they're going to put pressure on the PUC and blah, 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 blah. So bandwidth, remember, how many bits a second can I encode? That's one of the dedicated, that's one of the most important factors that indicate what kind of experience you're going to have. And then the other one is whether it's shared or dedicated with a lot of other people. So let's take a look at a couple in a little bit more detail. One of the technologies, and some of you may have heard of this because this was a technology that was dominant in the Houston area. It wasn't in all cities around the world, but we had a service for a long time called ADSL, and it may still be available in some areas. But ADSL was a technology that the telephone companies around the world adopted to try and bring you much higher speed access than they could with a modem, with a dial-up telephone modem, the thing that made those funny tones. So how did this technology come around to be the one that won the day? And it's worth taking a peek at what happened. So I'm going to switch back to my screen and pull up my drawing tablet, and we're going to take a little peek at it. So one way to draw what's happening on the copper wire is to make a note of the frequency ranges that it can support. You can run 1 gigahertz frequency sine waves on copper wire. The electrons will oscillate and correctly transmit energy from one end of the copper wire to the other at that wavelength, at that speed. So it's extremely high capacity wave, and you can send lots of data over it because the sine waves are very, very close together, and at every one of these you can make changes and encode ones and zeros. But you can also run a 100 megabit Ethernet network on it. You can also run 10 meg and maybe 1 meg, and the only thing the phone company used it for was to go from about maybe 50 hertz, it depends, up to maybe 3,000 hertz. Now 3,000 hertz is not the same unit of measurement as bits per second. I realize you can consider this in here to be about 55,000 bits per second for this range if you use the whole thing. So why did the phone company leave sitting on the table all of this capability up here? Why did they only use this? Well, because this is the only frequency range they needed to use to capture the human voice. People can speak and make noises up to 20,000 hertz, but you don't need to capture those and transmit them. You can lop them off the top and send them across this network, and people will still be able to understand what you're saying. So Bell Labs helped determine what those ranges were. So this has some huge advantages to the phone company because these relatively low frequencies tend to travel a longer distance than high frequencies do. They tend to be cheaper to build equipment to do. They don't need as much energy, so the batteries can be smaller. You used to have to have a battery at home to run your telephone, and before the phone companies supplied all the battery power from the other end of the cable. And it's also less prone to some of the interference and errors that you might gather with your phone cable, which after all is just a big giant antenna. So they built the entire world's network of telephony based on this. So between central office buildings, this is what would happen from your telephone at your house back to some piece of telephone company infrastructure. Between buildings, they're not going to take 10,000 users here and then have 10,000 cables here. First of all, not everybody's on the phone at the same time, but also it's extremely inefficient to do that. So they figured out ways of taking your signal here and moving it up a little bit so you can have one person here and one person here and one person here, and then they have to undo it at the other end when they got there. But that's not going to help you at all for trying to get to the internet because those are tricks that use more frequency but only between their buildings. That doesn't help you. You're sitting out here. You're on a network that's only using this bandwidth. So there were lots of schemes to try and fix this problem. We trialed lots of them in Houston. I was involved in many of them. We had companies that built things that were sort of industrial scale Ethernet that could handle hundreds of thousands of Ethernet connections, one to every user, but it required running an Ethernet cable out to their house. Then there were others that were fiber-based, which were like crazy high speed. But again, you had to run new cable all the way out to everybody's house. And so those things failed because there was no way for the phone company to really make its money back in time. And they don't want to throw away their network. I mean, they know they need faster network, but they'd like to preserve what they've got. So a company came along that recognized the dynamics of this, and what they also knew was how the money worked. And the way the money works in this industry is, if you remember the story I told you about the rancher 50 miles outside of Houston, and it cost you $1 million to put the phone in, and you can add that to all the money you spent this year, and then you divide it by the total number of subscribers, and it kind of goes into the average that everybody pays, so that everybody pays the same thing. Even if you're that rancher, you pay the same phone bill that somebody sitting right next to the building does. Well, one of the things that they have rules on is how much of that stuff can you charge the population back. So if you go and spend $50 million building out a bunch of new copper infrastructure, people shouldn't be asked to pay for all of that next year on their phone bills. After all, the copper is going to last a long time, and they're still going to have their phones after 1 year. It's not like they're going to have a phone for a year and then get rid of it. So at least for the longest time, that was the rule. So we're going to make you charge a little bit of it a year. In fact, we're going to make you wait 30 years to get paid completely back for that copper. But we will let you make profit during that whole time. So you become a very safe investment, but you've got a lot of stranded capital out there that you can't charge people for. So the last thing you want to do is put new cable out there and start a 30-year clock all over again. So that is a money, politics, and religion type of argument that most of the technology vendors who were trying to work in this arena didn't understand. In fact, it's incredible how little people understood about what was really going on. So a company came along and said, let's take your existing copper cable, and we know you guys have never paid attention to this, so who knows what we're going to find. We're going to find all kinds of problems. We're going to find places where you didn't connect the cables together tightly, and so it handles these frequencies well, but it can't do these. So we'll deal with a lot of issues we know, but it's going to run on the same cable. So what we're going to do is divide this spectrum up into bins, and we're going to draw them out like this, left to right. Each one of these things can generate about 40,000 bits a second, let's say, something like that. So if I can break this up into, say, 100 bins, then I can get 4 meg, 40 meg, something like that. So when I turn my device on, I'm going to add a modem to your house, a different kind of modem. I'm going to leave the phone line completely alone. I'm going to use higher frequencies only, and I'm going to start stepping through all of these frequency ranges and figure out which ones are good and which ones are bad because there's interference or there's a problem with transmitting that frequency, whatever it is. And what I'm hoping is I get enough of them that are good that if I add all of these guys up together, I can have a decent speed of network to give you. So I'm going to spread your bits out over all these independent little communication channels, and I'm also going to not divide it down the middle. I'm going to divide it so that a little bit of it is for upstream communication and most of it is for downstream communication. So it's not symmetrical, it's asymmetrical digital subscriber line technology. So that broke that barrier that the telecommunication providers had, and the company that was the dominant manufacturer, this Alcatel out of France, made billions and billions and billions of dollars by selling this infrastructure around the world. There was a huge need for it. The phone companies wanted to be able to provide you with high-speed internet access. While that's been going on and they've been making money, they've been pushing fiber closer and closer and closer, but they just didn't do it all at once. And many of us now have fiber all the way to the house. But this was enough to kind of get them going, and when they didn't feel like spending the money to put fiber all the way. In other parts of the country, they did it differently. In Verizon in New York, they ran fiber all the way to the house from the beginning because the population is so much more dense that the length of fiber on average they had to run was much less than what Southwestern Bell Telephone had to do in Texas, for example. Everything's bigger in Texas, right? You guys know that. So that's DSL. Another technology of this was that was used as an access network was one that the cable companies owned. They had a totally different perspective, and they had a totally different infrastructure. They had coaxial cable, which was super high capacity, and they had used that capacity from the beginning because they were trying to transmit hundreds of video channels simultaneously to all their subscribers. Though all the channels are always there on the coax cable, the only thing you're doing is filtering off which one channel you want to see on your TV at a time. But they're all there all the time. So that was a very high capacity network, and all they did was carve off some of the TV channels and dedicate them for upstream and downstream data. So that was ready built. They had a much easier time, and they hit the ground running much faster than the telecommunication providers in providing high-speed internet access, and had a much better product in the beginning. The only drawback was this was not a dedicated point-to-point circuit from the telephone company building to your house, and you had your phone line, and your next door neighbor had a completely different wire that ran all the way back separate. These were shared. So if you had a cable that ran through your neighborhood, it would go from house to house to house, or apartment to apartment to apartment, because after all, everybody had the same television channels to watch. So if we were all tuned into the Astros, we could all pull the signal off the same cable, that one signal. We don't need to send a different stream of Astros packets to every single user. So that caused some problems, and that they both had competitive products, and that's how lots of us got access to the internet. Okay, so moving on a little bit. Inside your home, you usually have one device that provides a variety of functions. It does Wi-Fi. It allows you to exchange traffic inside your home without having to go to the internet, like when you print a file to the printer, for example. But it also has a router that knows how to convert a signal coming in from the phone company and turn it back into packets and then get it back and forth. So it could be a cable modem or a DSL modem, and you can have some wired and wireless connections in here to get things back and forth and around the network. For enterprises, it's different. For institutions like the University of Houston, you have a very large network typically, and with many switches, and there's a need to divide the network up into isolated areas where everyone on campus doesn't see every packet that everybody generates. The network would be saturated, and we can't handle it. So one of the things that we build into most of the devices is some sort of switching technology. And what that basically means is the ability to look at a packet, look at its address, and decide, do I need to forward it on, or does it exist? Does the destination this user is trying to reach already exist on the local network, in which case I don't need to do anything? Or maybe I just need to forward it right over here nearby. So switches help suppress the needless propagation of data, and they have allowed networks to scale up to massive sizes. They're much less expensive to route than routers, and as we'll see, they're also self-learning. So they require much less administration, much less of a system administrator's, network administrator's time, and so they are popular choices. So networks like the University of Houston have hundreds and hundreds of switches flooded all over campus. At some point, there will be one or two core routers that sit at the edge of our network. There's more than two, but at the edge of the network, there's going to be a couple of routers with primary responsibility to getting traffic into and out of the institution overall. So the switches have the responsibility for making sure only the traffic that might need to leave gets here, and then the routers have the responsibility of getting it out to where it needs to go. And we'll look at more of those details when we get into the chapter on layer 2 and layer 3 devices. It's usually the case with these types of networks that you'll have more than one connection to the outside world, and sometimes there are fun tools you can use to kind of figure out how well connected you are to the outside world. And one of them I have here, let's see if I still have it open. Yes, I do. So let me switch over to uh.edu. And we're going to go to this website called Crater Labs. And what they do is look at the data to figure out how well connected you are to some of the core parts of the internet. And what you want to see is that you've got at least some diversity. So we're down here in the bottom left. This is our AS number, and we'll explain what that is this semester. And what I see is that I have connections to two different backbones. I have Metropolitan Fiber Networks, which is now part of MCI, and then, of course, Verizon. And then I have BCM, Baylor College of Medicine, because they sit over at something called the Gigapop in the Medical Center, where lots of educational institutions in Houston connect to get on a different backbone called Internet 2. And then you can see from there, they in turn connect to other people, and then they in turn connect to Level 3 and DTAG and GTT and NTT, which is Sprint, but was Japanese telephone company, etc. We can look at another institution if we want. We can go take a look at Rice up the street and see what their connection looks like. And this will build that graph. They connect directly to the NTT backbone and to level 3, and they don't connect to Baylor College of Medicine directly, but I wouldn't be surprised if I found something. I think this is the way they're going to get there, is through these here. And then if you take a look at somebody like, oh, I don't know, Google, what would you expect? What would you expect Google's map to look like? Only 2 links to the outside world? No, they're going to be heavily diverse. They connect to lots of different backbones around the country and around the world. Same thing if you looked at Amazon. So you can use tools like this, and I'll give you a chance, give you some problems to kind of explore some of these things so you can get a little better handle on what's going on. But that's what you're concerned about if you're a large institutional investor. On the wireless side of things, there are tons of different kinds of access networks. As we talked about last time, a lot of these things are licensed, particularly in the wide area network side of things, but lots of things are not licensed. I've hit the wrong button on my mouse. Sorry about that. It's drawing and drawing. Wi-Fi, for example, is part of the spectrum, but it's been prevented from being licensed commercially. It's restricted by the FCC for being put into the public domain, and it was by most countries around the world. So we can use our same Wi-Fi device, wherever we go on the planet. Okay, so how does someone actually send information? Well, a host sends data that's grouped together in clusters, in so-called packets of data. And the transmission rate determines how many of those bits a second can be introduced onto the wire, and therefore how long it's going to take to get a packet onto the wire. So if you give me an endless stream of data, we assume it's an infinite continuous stream of data. Periodically, I'm going to cut it into pieces and put it into a data structure. I'm going to make a function call to my socket library, and one of my arguments is going to be to pass along this data structure, and that's going to have a certain size. It's got to fit within rules. It can't be too big. It can't be too small. And if you continue this process ad infinitum, you're just going to be creating one packet after the other and introducing it to the network. And presumably you're going to have some packets coming back as well. So the time needed to transmit a packet that's got L bits in it is the number of bits divided by the transmission rate of the circuit. So that's going to tell you how much time. One of the most fundamental calculations you need. I used to do calculations for customers all the time based on nothing more complicated than this very simple formula. I had customers that would ask, I want to back up my data center from Phoenix to Houston every night as a second copy. I'm making a backup locally in Phoenix, but if something happens in Phoenix, I still need that data. So we would sit down and figure out how much data they had. And I was the guy that very often threw cold water on these arguments because the salesperson really wanted this customer to buy huge network to make this happen. But it's just not possible very often. The amount of data that customers generate is far in excess of what the networks of the world can carry. I don't care how many fibers you throw at the problem. Our ability to generate data still far outstrips our ability to transport it. So for the longest time, we use this joke about the network that carries more data than any other every night is Federal Express, because the fastest way to move massive amounts of data is to put it on tape and ship it in a FedEx box, because there's no substitute for that density and that speed and that cost as well. So there's still lots of backup that happens in sort of traditional old-style storage systems because it doesn't make sense to push it over the network. I have a little RAID array at my house with photos that I've taken working in the evenings for the newspapers as a sports photographer for years. And I signed up for one of these backup services that will run continuously and will constantly capture things that are changing, et cetera. And I have a gigabit connection at my house. Their little algorithm said it would take 2.3 years to make the first backup. It just doesn't work for lots of things. So don't believe that networks will solve all data movement requirements that you have. And we may have a chance to talk about some other interesting things. So one of the things I wanted to go backwards to and show you guys was a diagram from this other book because it shows something that we're not going to see in our book for quite a while. It shows kind of the way things look today with this hierarchical organization of networks. So you have your local access networks. This would be your local ISP, PDQ.net in the old days, et cetera. And then regional ISPs. Very often these are one and the same now. It's going to be your telephone company, your cable company. But the question arises, how big are they? And with all of the variety of destinations that you guys are throwing at the internet of where packets are going to need to go, to how many of those other networks does your ISP directly connect? Because if it has to pass everything through 15 other steps along the way, that slows everything down. It takes more time for your packet to reach your destination, and it adds latency. So it makes the round trip take longer. It makes the web page take longer to load. It makes the movie take forever to get there. It takes longer to exchange chat messages, etc. So this is a profound problem because these small ISPs would like a chance to compete with the big guys as well. And even some of the larger ISPs still need to exchange data with lots of other people. So there's a couple of ways of going about it. One way to go about it is everybody connects to everybody else. And so you end up with a full mesh, and then this person connects to everybody as well. And phone company salesperson would love that because then you're just buying everything that's possible. But that's not feasible. So this is not going to work. So the other way to do it is what we do, which is you connect to a few people in your region that you exchange lots of data with, like we saw with U of H and Rice. They connect to something in the sort of in the region because there's lots of traffic between Rice and U of H and the medical center schools because we have research grants together and we know each other and things like that. But then you'll connect to a neutral third-party territory, an Internet Exchange Center or a network access point, and that's what NAP means in this diagram. And this is a place where not only all the locals connect, but anybody who is a national or international sized ISP that wants to reach lots of customers easily in that metropolitan area, they can also come here. So Amazon can connect to this, and Microsoft's backbone can connect to this, and Google will connect to this. And so will all of these other names like Hurricane Electric and Level 3 and anybody that wants to get traffic exchange. So for these guys, it's fantastic because now all of their users are one hop away from any of these providers' backbones, and they never had to pay to connect to them directly. They had to pay for one big connection to this building, and it's the cost of a $10 piece of fiber to run a cable from the router in my rack to the cable in your rack. So it cut the bottom out of the cost of doing this stuff, and it's great for these guys because all the users are here. So if you connect to just this one place in Houston, then you have access to all of these ISPs with all of the millions of users they've got, including the cellular providers are connected here as well. So back to the Hurricane Electric website that we were looking at a little bit ago. You'll notice they mention these addresses of all these places they connect to around the world. And one of them in here is Equinix Los Angeles LA1 at 600 West 7th Street in Los Angeles. So let's go to Maps and look for Equinix in Los Angeles and see what we can find here. And so I've looked at this in the last couple of days, so it's already kind of in satellite mode. And I'll get rid of this. And here's a building where this stuff is all happening. And one of the things we're going to do in class this semester is I'm going to get you guys used to spotting large national communications infrastructure when there's not a lot of things to give you obvious hints at what's going on. So I'll point out a few things here that are different about this building than the ones around it. First of all, it's a big building. I mean, this one's big over here on the right as well, but it's definitely big. But if I look at sort of this big building, I see a really big parking lot, and I can tell that there's a lot of cars here, but also from the dark markings, there's usually even a lot more cars here. So maybe this picture was made on a Saturday. When I look at the Equinix building, and I look at their parking lot, I don't even see stripes. It doesn't look like anybody's parked here in years. At the other end of the building, there's a few parking spaces These don't have any kind of oil spots and stuff. There's a few cars here. So that's one hint that there's something going on in here that doesn't need a lot of people. There's a huge diesel tank for refueling generators. There's massive air handling, and there's an incredible power distribution system here. This is basically an electric utility substation. And I also notice if I look around, I can't really tell what this pole is, but I can tell if I look at the shadow. These are power and communication poles. Look how long this shadow is. This is a site getting tons of power. In fact, it's on both sides of the building, on both sides of the street. And if I go to the street and look, one other thing you notice is there's no sign whatsoever of what's going on. And yeah, they do have some glass, which is also very unusual to see. So maybe they have a few offices over here, but there's no signage anywhere to tell you what's going on. And look at the power around this thing. So this stuff doesn't add up to be just your normal warehouse distribution center. And then the last thing I'll point out to you, and then we'll be able to take a hike here today, is if I go around the parking lot, I'm going to look for manhole covers. That's, you know, some people look at the floor or look at the ground as they walk around the city looking for pennies. I'm always looking at the ground. I'm looking for manhole covers, and I have pictures of thousands and thousands of them from around the world. So here's a manhole cover. Here's a manhole cover. If I go to this side of the building, another one, another, two more here, 1, 2, 3, 4, 5, 6 more here, 7, 8. Complete total overkill for any kind of industry other than the sewage treatment plant and a communications data center. And what we'll look at this semester are some communication bunkers that sit at the edge of the coasts and drive undersea cables to China and Japan and Europe. And you'll look at how quasi-military they appear to be. So we'll have some fun looking at that stuff. You guys will get to explore back to that map I showed you earlier of that undersea cable network. So we'll play around with a little bit of that. That's all we've got time for really today. I want to give you guys a chance to get to your next class, and I'll see you back in person 8:30 on Tuesday in Houston, and I'll stick around in case there's a few questions. I'll keep my eye on chat here. Bye, everybody. The manholes are there because that's where cables come near the building. And then the way you take cables that are inside the building and you connect the two together is you go down under the ground and connect the cables together in a big manhole. So it's basically a big vault. It's like a room, and you've got places for electronics in there, and you've got wall space where you can connect cables and fibers together. And so you can either do it above ground in the air and do all of your splicing in little insulated boxes, these big fat blobs that you find every so often along the telephone lines, or if you want to be safer, you can do it underground. Costs more, but it's less prone to being hit by a car or, you know, torn up or dug up if you're paying close attention to it. Yep, land wires. My life underground. I'll see if I can find some pictures of what happens in manholes as well. All right. I think that's looks like there's more coming in. Have a great weekend, guys. Talk to you. Bye-bye. Thank you.